So when evaluating these, notice we have the function notation. Notice in number 1 here, it's asking find f of 5. The 5 is in the parentheses, meaning that we're going to plug the 5 in for x, because x is normally in the parentheses. So first step, write out f of 5 equals 3 to the 5th plus 1. We're just replacing the x with the 5. Now we got to go through order of operations to figure out what this equals. So we got an exponent and we have addition. Which comes first, exponents or addition? Exponents. Exponents, absolutely. So the very first thing we do now, we do 3 to the power of 5. Now I suggest that you do this on a calculator that actually has an exponent button. Because if you're doing 3 times 3 times 3 times 3 times 3 on your calculator, 1, you might make a mistake. 2, it's going to be really hard when I have you doing it 20 times instead of just 5. So you do 3 to the power of 5. That gives us 243. So now we're going to do the 243 plus 1. And so f of 5 equals 244. That's our basic process. You're going to repeat that process there for number 2. So go ahead and tackle number 2 now. All right, so in order to figure out what this equals, notice we have a of 10. The 10's in the parentheses, therefore we're going to plug it in for x, which was in the parentheses. So a of 10 equals 4 times to the 10th. Now we have multiplication, we have exponents. Which comes first, multiplication or exponent? Exponent. Absolutely. All right, so first thing we're going to do is we're going to go ahead and deal with that exponent. That gives us 1,024, and we do 2 to the 10th. All right, so now having done the exponent part, now we do the multiplication. So we're going to do 4 times the 1,024. So our final answer here, a of 10 equals 4,096. Having done those, you now should be able to do these last 2. And then after we do these, we're going to get into our main topic for the day, but this is laying that foundation for it. Now, as you work this first one, of course, we're plugging 8 in for the variable. In this case, the variable happens to be called t. That's okay. We're still just going to plug the 8 in for t. So our first line, a of 8 equals 2 times 5 to the power of 8 minus 6. Now, just to be super clear, the 8 minus 6 is all in the exponent here. If I was going to be putting parentheses in, I could write this with parentheses around the 8 minus 6, and it would mean the same thing. Since the 8 minus 6 is all in the exponent, we have to do that first before we can actually do it to that power. So do the 8 minus 6. So now we have 2 times 5 squared. Then we can go ahead and calculate the value. It's just we want to be clear on that order of operations, because that one can be a little funky because it seems like we're doing the subtraction first, but really it's going under parentheses. We just don't have to draw the parentheses in here. So the next thing we do the exponent before the multiplication. So 5 squared gives us the 25. Now we can go ahead and do the 2 times the 25. Final answer there, a of 8 equals 50. And the last one, number 4 here. We're plugging 30 in for m here. So it's going to be our exponent. So we have p of 30 equals 100 times 1.1 to the 30th. This is definitely calculator work here. So first thing up, do the 1.1 to the power of 30. When we do the 1.1 to the power of 30, you end up getting a decimal. If we start with a decimal that we're raising to a power, you're going to end up with a decimal. It actually gets to be an uglier and uglier decimal as we go. It ends up being about 17.4494, and it just keeps on going and going and going. One thing I want to draw your attention to in terms of how I've written that, since I rounded that, you notice that that equal sign there is a little wavy. A wavy equal sign means approximately equal to. So it just means that we've done some rounding here. It's one of those little things that we can do to be a little bit more clear in our math and in our writing that we do for it. All right, so now that we've done that, we can go ahead and do the 100 times that number. And so we get a final answer here of 1,744 I took it to 94, 2 decimal places. You could take it to more, of course, if you wish. So today we're going to be writing equations for and solving problems that look like this. Now you notice in this one, a number of branches of a certain type of tree doubles every year. The tree starts with one branch. Why one? Because it was easy. How many branches will it have after 20 years? One thing I want you to note, what makes this important here is that the number of branches is doubling every year. In other words, we're multiplying the last number by something when we go to find the next one. And that's going to tell us what type of function to use. Now, before we get into it, write down the problem. In order to figure out how to write an equation for this, we're going to start by just saying how do we calculate it if we were trying to do it the long way. So to start with, in year 0, that is the starting year, we have one branch. That was given to us in the information up here that we just had one branch. Year 2, or I'm sorry, actually at the end of year 1, so end of the first year, we're going to have 2 branches because remember we're doubling each year. And so I'm taking whatever the last one was and I'm going to multiply it by 2. So after 1 year, there's 2 branches. After 2 years then, there would be 4 branches because I'm just multiplying the last one by 2. After 3 years, there would be 8 branches. And we can just keep going through this pattern over and over again, multiplying the last value by 2 in order to be able to find our value. Now the problem with this method, if we're going to try to just rely on this, is that we're trying to figure out how many branches will be there after 20 years. We don't really want to have to do this 20 times. One, it's a lot more work than it has to be. And 2, it's prone to errors. It's very easy if you're just saying times 2 times 2 times 2 to make a typo or to miscount. You know, we get distracted partway through all the times we're saying times 2 times 2. It's not a very good method to rely on just saying times 2 over and over and over again. Instead, then we can actually figure out how to calculate these values. So we're going to see how could we calculate this and then eventually use that to write an equation. So first up, the way we start calculating these is, of course, the first in year 0 is just 1 because that's what we start with. For the end of the first year then, we do 1 times 2 because we had to figure out what that last number was times 2. Now if I want to know what it is the year after that, I'm then going to take this number and multiply it by 2. Or the year after that, I take whatever this number was and multiply that by 2. And of course, we can just keep going on and on and on with this same pattern. And it just would keep getting bigger and bigger. Every single year, we're just adding a 2 to it that we multiply by. So notice what we actually have then in year 10. Notice in year 10, I start with 1 because I started with 1 up here. And then I multiply it by 2's. And in this case, there's 10 2's because it's 10 years later. But I don't want to have to type that in my calculator because, again, that could be prone to error, especially when I get up to 20 of them. So then, what's a shorter way to write 1 times 2 times 2? Well, 10 2's together. 2 to the 10th, yeah. So instead of 1 times all those 2's, we could just write this as 1 times 2 to the 10th. Well, and we really can do that for all the other ones too, right? So all of those other ones, rather than 2 times 2, we write as 2 squared. 2 times 2 times 2 becomes 2 cubed, etc. So as we look down this list then, you notice everything's the same except the exponent. That's going to make writing the equation a lot easier. Now, just for clarity's sake, you notice these top 2 don't necessarily look like the rest, but they actually can. Because like 1 times 2, this 2, that's just 2 to the power of 1. And 1 up here, that's actually 1 times 2 to the 0. Because remember, 2 to the 0, anything to the power of 0 is 1. So that's why it still works there. So being able to see that that then works every single time, we can actually look to write an equation for this. So here's all of our information. Notice as I look down this list here of the calculations, the 1 is the same every single time. The times is the same every single time. The 2 is the same every single time. The only thing that's changing is the exponents up here. And you'll notice that the exponents are exactly the same as the number of years. That makes writing the equation actually pretty easy. It's just that if I'm going to write an equation, I need to pick some variables here. So I'm going to choose a variable for years, a variable for branches, and then I'll actually be able to write my equation. For years, I'm going to use the variable t. Now you could use y for years, but traditionally t is always used for a measure of time, be it years, days, months, minutes, whatever. We tend to use t for that. So it's a nice default. I'm going to stick with it. So t is going to represent the number of years. Branches. The number of branches, I do like to use a letter that really represents what it means. So I'm going to go with B for branches. Always go with a letter that means something. Don't just go with old X and Y, or you'll very quickly forget what they actually represented. And so now I know what the variables are. I can go ahead and write my equation. And remember that my equation tells me what the number of branches are. So I know it's going to be B equals, because it tells me the number of branches. And then I can write my equation. And again, notice in our equation, the 1 was always the same. So I'm going to have a 1 there. The times was always the same, so I'm going to have a times. The 2 was always the same. Everything that stayed the same, we just put in the equation exactly as it was. The only thing that didn't stay the same was the exponent. So the exponent is then going to have to be a variable. And remember that since it was exactly the same as the number of years, it's just going to be t. So there we've written an equation for it. So b equals 1 times 2 to the t. Knowing that, I can now go back to the original problem and solve it without having to type equals over and over and over and over again in a calculator. Because now I can just take my 20 years and plug it in for t. So we're going to do b equals 1 times 2 to the 20th. Go ahead and figure out what that equals. All right, so in order to figure out that value, we do 2 times the 20th. I'm sorry, 2 to the power of 20. Say it better. That gives us a bit over 1 million. If I do 1 times that number, of course it gives me the same thing. So our final answer here is over 1 million branches. 1,048,576 to be precise. Next up, we're going to vary that last problem just a little bit and see how that would affect our equation. In this problem, this is the exact same problem as what we just did, except they were starting with 7 branches instead of starting with 1 branch. Otherwise, this problem's the same. So the question then is, how would I write that equation? Well, let's take a look back at the work that we did last time first. So I know that something's going to need a change in this whole series. Now, you may already see it, which would be excellent. But if not, let's actually take a look at the numbers and see what that does. So in this particular problem, in year 0, I have 7 branches because, of course, we start with 7. We're still doubling the number each year. So my next one's going to be 14. So that means that I ended up doing 7 times 2. Okay, and then if I double that, I get 28. If I double that, I get 56. Do you already see the pattern, though? Because it was 7. Then we did 7 times 2. Then we did that times 2. And then for the last one, we did that times 2. Notice it's the exact same thing as what we're doing over here, except it's not 1 times the 2's, it's 7 times the 2's. And so then that tells us something about how we can write these equations a bit more efficiently. All right, let's go ahead and write this equation. You'll notice the 7 is now there in place of the 1. Otherwise, it's going to be the same equation as what we saw before. So it's going to be b equals 7 times 2 to the t. Now that we know the equation, we can go ahead and solve this problem. So go ahead and figure out what 7 times 2 to the 20th is going to be. All right, so we end up doing 7 times that 1,048,576, which, by the way, you already had from the last problem, so it probably made your life a little easier. Then we're going to multiply that by 7. Your final answer here is a bit over 7 million. 7,340,032 to be precise. So already we've seen how we can vary our equation, but we are going to vary it one more way. And so we're going to go through one more problem here together. In this problem, I decided to switch away from branches because they can't all be about branches. In this case, we're going to look at a colony of bacteria. These sorts of things actually come up a lot in biology, so it's actually a good example to be bringing up. In this particular very simple example, our bacteria population is going to be tripling every day. So in other words, we're going to be multiplying it by 3 this time instead of multiplying by 2 each time. And we're starting with 120 bacteria in our sample. The question is, how many bacteria will there be in 10 days? We're going to approach this the same way as we did the last one by writing an equation. Now, in writing an equation, it often is very helpful to start by thinking about how would you calculate the value the long way. So how would I actually go about doing that? Well, after 1 year, we'd do 120 times 3. After 2 years, that'd be 120 times 3 times 3. After 3 years, we'd be multiplying 3 times. Oh yes, days, sorry, thank you. Yep, this one's days, not years, thank you. So then after 10 days, though, notice what this equation would look like, what the expression is. So I'm doing 120 times 3 times 3 times 3. There's 10 3's there. What's the short way to write that equation? Right, it is 120 times 3 to the 10th. So when you're dealing with story problems, one of the great ways to go about it is if you don't know what the equation looks like right off the top, think about how would you calculate it the long way and then use that to write it. All right, now for this one, we know our calculation that we're going to have to do. We're going to do 120 times 3 to the 10th. Please do that calculation. Figure out how many bacteria are going to be there after 10 days. All right, so when we go to do this calculation, again, we do the exponent first. So I'm going to do 3 to the 10th, which gives us 59,049. Multiply that by 120, and you find that we end up with 7,085,880 bacteria in this sample after that. So 10 days later. Now, you've now seen a number of different ways of doing these equations. With more and more things being varied, we actually can have a general formula that you can plug stuff into that relates to that. And this is going to go into your notes next. Add this into your notes. This tells you that we're going to be writing exponential equations, that is, anything with the variable in the exponent. Anytime we keep multiplying from 1 year to the next, or 1 day to the next, whatever it is, we're multiplying every time through. That tells us to write an exponential. And you can see there the general exponential formula. Put that into your notes with all the little details.